this video we're going to explain a little about CT, not too detailed, but a little some technical issues. Computed tomography. Computed tomography, or just CT, is a three-dimensional reconstruction of the bodily structures of a person's inside. Created in 1972 by Godfrey Hounsfield and Alan Cormack. But how is it done? Imagine we have a sphere and we take a picture of it from the XY axis. It will look like a circle, but we cannot know if it's a sphere or a cylindrical object. Then we could take a picture from the Z object, but from the YZ axis, and combine it with the previous picture. If the picture on the YZ axis looks like a circle, then we can say it's a sphere. This is the same process used in computed tomography. We take an X-ray image in several angles. Then we use computerized algorithms to process these images in order to get a three-dimensional reconstruction of these images that represent the internal structures of a patient. The problem with an X-ray is that it lays a two-dimensional image. You can know a little bit about the object, but you cannot know the dimensions of the depth of the object. This is why we use CT, because it takes X-rays to reconstruct a three-dimensional image. Okay, we're going to explain a little about the equipment and how does this works. Well, suppose we have a X-ray emitter, and we have a detector of a panel. These two are in a gantry, and this rotates or spins all around a table where the person is laid down. This spin allows us to visualize the image from different angles. Then the processing image software, what it does is take the pictures and arrange them to reconstruct and to give us a three-dimensional image of the objects. There are different generations of tomographs. The first generations of tomographs consist in 1 to 2 detectors. Now, the modern tomographs, 4th through 6th generation, consist in nearly 5,000 detectors located in a concentric ring. And they normally use the helicoidally scanning technique in order to shorten the modern CT uses a helicoidally movement. This is mainly because when you have the gantry and you have the X-ray and the detector spinning and they do a 360 movement, they use a lot more of processing, and the times of both are of helicoidally in contrast to 360 movement is very, very fast and very easy to process, and also the data of helicoidal movement is much less, and the space and the format and everything is a little more efficient than the 360 ways. These movements focus on spinning the X-ray a little like 180 degrees. This just spins like a semicircle, and then the detector moves into another position. This it's more efficient, and it takes less time both to process and to take the analysis of the person, and this proves that a helicoidal movement is much more efficient than the old way. There are little boxes called box cells that contain the information, the 3D information, because they also contain the volume, and they contain the coefficient of attenuation of every tissue or tissues by what the beam passes. Every voxel has a different constant of attenuation. This constant is how the tissue absorbs the radiation. In this example, imagine we have a tissue, high-density tissue like a bone, and this bone don't absorbs most of the rays because it's a high-density tissue. So the coefficient of attenuation of that tissue is, as we expect, very high. And suppose we have low-density tissue like, I don't know, a lung. As we know, a lung is almost all made of air, and air is lets the beam passes almost completely. If we know the coefficient of this lung, we will know that the coefficient is very, very low. I mean, the beam almost passes completely. Then the voxel has all the information of different constants of attenuation of different tissues. We can have different values, and what the algorithm does is that we can, for example, depending in the position of the beam, where the beam passes, we have different sums of the values. I mean, for example, I don't know, 4 plus 1 or 3 plus 1 or 8 plus 1, and it depends on the angle of the beam and the orientation. Then the algorithm, what it does is that sums all of this, and in the end we have a number of equations, but with the same variables, and that lets the algorithm tell or solve that equation. As we know, if we have different values or coefficients and we have the same number of equations, we can rapidly solve that equation and know the values of each one of that coefficients. The dimensions of this voxel depend on the length and width of the detectors. We use Hounsfield units, or HU, to determine the contrast of color of every structure. This Hounsfield unit takes the water attenuation coefficient as a reference to obtain the contrast of all other structures. The reason for this is because the body contains a large amount of water, and every structure has an attenuation coefficient in relation to that of the water, being water Hounsfield units value 0. Since we cannot obtain the full range of bit values for a normal monitor to display, we use something called a window. A window is used in order to visualize just a range of Hounsfield units in order to be able to see certain structures with specific Hounsfield unit values. Since the contrast range we are able to see is that of 0.5%, we are able to distinguish up to 5 HU, or 2 levels of contrast, obtaining a spatial resolution between 0.25 to 0.5 millimeters, with an actual acquisition time of 5 seconds. The conventional gantry diameter is 728 centimeters by 2 meters. In mathematics, the radon transforms in 2 dimensions, named after the Austrian mathematician Johann Radon. Is the integral transform consisting of the integral of a function over straight lines, as we use in CT. We have 2 ways that modern CT uses. One is the inverse Radon transform, and the other is the fan-like way. In the Radon inverse transform, the beam passes like parallel one to another. I mean, it's a straight beam. It do not deviate or do like a triangle shape. That's the fun way. The beam are all directed to a single target, and the way it's like a triangle or like a fan way. The inverse radon transform is a little more efficient, and CT of latest generations use this because efficiency mostly. In bottom left we have an image. It's like image of CT. It's as you can see by colors. This display the range of colors of the density of the tissue. You can see with the tissue being more dense, the color, the spectrum of the color is a little more white. I mean, if the tissue is much more dense, like a bone, in the image we will see a color white. If the tissue is like, I don't know, a lung or a vacuum, or there's just nothing there, we can't see a dark or a black color. And this passes through a spectrum of red and yellow colors. Red symbolizing low dense tissues, and yellow symbolizing high density tissues.
As it happened, an old lathe bed was available in the lab, and by using discarded equipment also found around, I was able to build this lab test machine which would demonstrate the principle of the system.
Tests begin on a rig built from an old lathe. X-ray data is fed into a computer. Would it show up density differences in animal tissues as well as it does on the Perspex model? Hansfield searches for specimens where he can find them.
I had to go around to abattoirs and cut out brains from cows, but unfortunately these were damaged by their method of killing, so that we found ourselves travelling across London to the Jewish kosher houses, which they killed by bleeding the bullocks. And it was quite a job carrying these across London in a paper bag to put on the machine. The ventricles did show up very well. Job carrying these across London in a paper bag to put on the machine. The ventricles did show up very well, and it was just a matter then of making a clinical machine.